For decades, humanity has been shouting into the darkness of space. We have beamed radio signals toward distant stars, launched golden records into the void, and spent billions searching for a reply. We assume that finding intelligent life would be the greatest discovery in human history, a moment of wonder and unity. But what if that assumption is catastrophically wrong? What if the universe is not empty at all, but full of civilizations that have already learned one terrifying rule: stay silent or die? There is a theory that reframes the silence of the cosmos not as loneliness, but as a warning. It suggests that the most dangerous thing a civilization can do is announce where it lives, and we have already done it. If you enjoy journeys that challenge how you see reality, hit that like button and subscribe. It genuinely helps this channel keep exploring the strangest and most important questions about our place in the universe. Now settle in, get yourself comfortable, let's begin. Every civilization that has ever looked up at the night sky has asked the same question: are we alone? The question predates telescopes, predates science, predates written language itself. Ancient Greeks debated whether other worlds existed beyond Earth. Roman poets imagined inhabitants on the moon. Medieval philosophers argued over whether God would create a universe so vast and populate only one small corner of it. The question has followed humanity through every stage of its development, evolving from mythology into philosophy, from philosophy into science, from science into one of the most ambitious technological searches ever attempted. And for most of human history, the answer seemed obvious. Of course, we are not alone. The universe is too large, too old, too rich with possibility for Earth to be the only world where something opened its eyes and wondered what the stars were made of. This intuition gained scientific credibility in the 20th century. As telescopes improved and astronomers began to understand the true scale of the cosmos, the numbers became staggering. Our galaxy, the Milky Way, contains somewhere between 200 billion and 400 billion stars. Many of those stars are older than our Sun, some by billions of years. The observable universe contains roughly 2 trillion galaxies, each with its own population of hundreds of billions of stellar furnaces. The sheer arithmetic of existence seemed to guarantee that life, including intelligent life, must have arisen elsewhere. In 1961, astronomer Frank Drake attempted to put numbers to this intuition. Working at the National Radio Astronomy Observatory in Greenbank, West Virginia, Drake developed an equation designed to estimate how many communicative civilizations might exist in our galaxy at any given time. The Drake equation, as it became known, multiplied together a series of factors: the rate of star formation in the galaxy, the fraction of stars with planetary systems, the fraction of those planets that could support life, the fraction where life actually develops, the fraction where intelligence emerges, the fraction that developed technology capable of sending detectable signals, and the average length of time such civilizations continue broadcasting. The equation was never meant to produce a precise answer. Many of its variables were unknown in 1961, and several remain poorly constrained even today. But the equation accomplished something more important than a single number. It made the search for extraterrestrial intelligence feel scientific rather than speculative. It gave researchers a framework, a set of questions that could be investigated one variable at a time. And when you plugged in even modestly optimistic values, the result was striking. The galaxy should contain thousands, perhaps millions, of civilizations capable of interstellar communication. The universe should be teeming with voices. This optimism fueled one of the most remarkable scientific programs in history. The search for extraterrestrial intelligence, known as SETI, began in earnest in 1960, when Drake himself conducted Project Ozma. He pointed a radio telescope at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for artificial signals. He heard nothing, but the idea that humanity could listen for alien civilizations using existing radio technology captured the imagination of scientists and the public alike. For the first time, The ancient question of whether we are alone became a question that could be pursued with instruments rather than arguments. Over the following decades, the search expanded dramatically. NASA funded dedicated programs. The Ohio State University's Big Ear radio telescope scanned the skies continuously for years. Private organizations like the SETI Institute, founded in 1984, built world-class research programs around the search. The Allen Telescope Array, funded by Microsoft co-founder Paul Allen, was designed specifically to accelerate the hunt for extraterrestrial signals. And in 2015, Breakthrough Listen launched with $100 million in funding from Russian-Israeli investor Yuri Milner, becoming the most comprehensive SETI initiative ever undertaken. Breakthrough Listen surveys millions of stars across multiple frequency bands, processing vast quantities of data with algorithms designed to identify patterns that could indicate an artificial origin. And there were moments, scattered across those decades of listening, when the dream of contact seemed to brush against reality. On August 15, 1977, astronomer Jerry Eman was reviewing data from the Big Ear radio telescope at Ohio State University when he encountered something that stopped him cold. The telescope had recorded a narrowband signal so strong, so cleanly defined, and so precisely centered on the hydrogen frequency that SETI researchers had long predicted aliens might use for communication, that Eman circled the data printout in red ink and wrote a single word in the margin: "Wow." The signal lasted 72 seconds, matching the exact duration that a fixed radio source would produce as the Earth's rotation swept the telescope's beam across the sky. It came from the direction of the constellation Sagittarius, from a region of sky containing no obvious natural source. It was never detected again, despite hundreds of subsequent attempts to relocate it using instruments far more sensitive than Big Ear. The WOW signal remains the strongest candidate detection in the history of SETI. It has never been explained to universal satisfaction. A 2017 study proposed that it might have originated from hydrogen emissions associated with comets passing through the telescope's beam, but this hypothesis was contested by other researchers, who argued that the signal's characteristics were inconsistent with a cometary origin. No natural explanation has achieved consensus, and no repetition has ever been observed. The signal appeared once, tantalizingly consistent with what an artificial transmission might look like, and then vanished into the noise as if it had never existed. Decades later, another candidate surfaced from an entirely unexpected direction. In 2020, researchers working with the Breakthrough Listen project detected a narrowband radio signal designated BLC-1, originating from the direction of Proxima Centauri, the closest star to our Sun. The signal appeared at a frequency of 982 MHz, a range not commonly used by known terrestrial sources and not associated with any obvious natural astrophysical process. It exhibited a slight frequency drift consistent with a transmitter located on a planet or object in motion relative to Earth, precisely the kind of signature that SETI searches are designed to detect. For months, as the detection was analysed and verified, the scientific community held its breath. Proxima Centauri is known to host at least 2 exoplanets, one of which, Proxima Centauri b, orbits within the star's habitable zone. The possibility that a deliberate signal had been detected from the nearest potentially habitable world to Earth was electrifying, but subsequent analysis, published in 2021, determined that BLC-1 was almost certainly a product of terrestrial radio interference, likely generated by electronic equipment near the telescope itself. The signal's characteristics, while superficially intriguing, were ultimately consistent with a human-made source rather than an extraterrestrial one. The resolution was disappointing but instructive. BLC-1 demonstrated both the power and the fragility of the search. It showed that existing instruments are sensitive enough to detect faint narrowband signals from the direction of nearby stars. It also showed how easily terrestrial interference can mimic the signatures that SETI researchers seek, and how rigorously candidate detections must be vetted before any conclusions can be drawn. The signal was not evidence of alien intelligence, but the brief period during which it might have been revealed just how deeply the scientific community and the broader public wanted it to be real. There have been other tantalizing anomalies over the years. In 2015, astronomers noticed unusual dimming patterns in the light curve of a star designated KIC 8462-852, informally known as Tabby's star, after astronomer Tabetha Boyajian, who led the study. The star's brightness dropped by as much as 22% at irregular intervals, far more than could be explained by a transiting planet. Some researchers speculated that the dimming might be caused by a megastructure, an enormous artificial construction partially encircling the star to harvest its energy, a concept known as a Dyson sphere or Dyson swarm. The hypothesis was taken seriously enough to warrant dedicated SETI observations of the star, searching for radio emissions or laser pulses that might accompany such a structure. No artificial signals were found, and subsequent studies concluded that the dimming was most likely caused by clouds of dust orbiting the star. But the episode illustrated how hungry the scientific community was for evidence that someone else was out there, and how willing serious researchers were to investigate even exotic possibilities when the data warranted it. Each of these near misses reinforced the same emotional pattern. Hope surged, analysis tempered it, and silence reasserted itself. The WOW signal, BLC1, Tabby's star, each one momentarily cracked open the door to a universe populated by other minds, and each one gently closed it again, leaving humanity exactly where it had been before, listening, waiting, alone with its instruments and its longing. Meanwhile, the case for a populated galaxy grew stronger every year from an entirely different direction. The exoplanet revolution, which began with the first confirmed detection of a planet orbiting a sun-like star in 1995, accelerated through the early 21st century at a pace that astonished even optimists. The Kepler Space Telescope, launched in 2009 and operational until 2018, discovered more than 2,700 confirmed exoplanets. By monitoring the brightness of over 150,000 stars and watching for the tiny dips in light caused by planets crossing in front of their host, stars, the Transiting Exoplanet Survey satellite, known as TESS, launched in 2018 and extended the search to nearly the entire sky, discovering thousands of additional candidates, including rocky worlds orbiting nearby stars. Among the most remarkable finds was the TRAPPIST-1 system, announced in 2017. This ultra-cool red dwarf star, located approximately 40 light-years from Earth, hosts 7 rocky planets, at least 3 of which orbit within the star's habitable zone, the region where surface temperatures might permit liquid water. 7 worlds around a single small star, 3 of them potentially capable of supporting life, orbiting close enough to Earth that their atmospheres can be studied with existing technology. The system became a prime target for the James Webb Space Telescope, which began observations in 2022. JWST has already begun probing the atmospheres of TRAPPIST-1 planets and other nearby exoplanets, searching for molecules that might indicate biological or geological activity. Early results have been cautious but compelling. The telescope detected strong evidence of an atmosphere on the rocky exoplanet 55 Cancri, and identified intriguing chemical signatures on several other worlds. The detection of dimethyl sulfide in the atmosphere of K2-18b, a sub-Neptune exoplanet roughly 120 light-years away, drew particular attention because on Earth, dimethyl sulfide is produced exclusively by living organisms. The finding remains preliminary and contested, and alternative non-biological explanations have not been ruled out. But it demonstrated that the technology to search for biosignatures, chemical evidence of life on distant worlds, is no longer hypothetical, it is operational. The cumulative picture was extraordinary. Planets were everywhere, habitable worlds numbered in the billions within our galaxy alone. The chemical building blocks of life were universal. The instruments to detect signs of biology on other worlds were already in orbit. Everything pointed toward a cosmos rich with the preconditions for life. And yet the silence continued. No confirmed signals, no unambiguous technosignatures, no evidence that any of those billions of potentially habitable worlds had produced anything that looked back at us and said hello. The numbers screamed that we should not be alone. The data whispered that we were. The assumption underlying all of these efforts was fundamentally hopeful. Scientists believed that if intelligent civilizations existed out there, at least some of them would want to communicate. They would build radio transmitters or powerful optical lasers. They would send signals outward, either deliberately as beacons or accidentally as leakage from their own technology. And if humanity listened carefully enough, with sensitive enough instruments pointed at enough stars for enough time, eventually we would detect something, a carrier wave, a repeating pattern, a sequence of prime numbers that could not be produced by any known natural process, something that would change everything. But humanity did not only listen, we also called out. On November 16th, 1974, astronomers used the massive Arecibo radio telescope in Puerto Rico to send humanity's first deliberate interstellar message. The transmission lasted less than 3 minutes. It contained 1,679 binary digits arranged in a rectangular grid that, when properly decoded, depicted a stick figure of a human being. The numbers 1 through 10, the atomic numbers of key elements in human DNA, a graphic of the double helix, a schematic of our solar system with Earth highlighted, and an image of the Arecibo dish itself. The message was aimed at Messier 13, a dense globular cluster of roughly 300,000 stars located approximately 22,000 light-years from Earth. Even travelling at the speed of light, the signal will not arrive at its destination for another 25 millennia. A reply, if one ever came, would not reach Earth for 50,000 years. The Arecibo message was more symbolic than practical, a declaration that humanity was ready to speak to the cosmos rather than a serious attempt at conversation. But symbolism matters. The act of sending that signal represented something deep and instinctive about human nature. We wanted to be heard. We wanted to be known. We assumed, almost without thinking, that being known was a good thing. 3 years later, in 1977, NASA launched the twin Voyager spacecraft on trajectories that would eventually carry them beyond the boundaries of our solar system and into interstellar space. Each probe carried a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. The records included spoken greetings in 55 languages, samples of music from cultures around the world ranging from Beethoven to Chuck Berry, natural sounds like thunder and birdsong and the calls of humpback whales, and 116 images depicting everything, from human anatomy and architecture to landscapes and scientific diagrams. Critically, each golden record also included a pulsar map showing the position of our Sun relative to 14 pulsars, providing any finder with a precise cosmic address for our home star. The cover of the record displayed instructions for playback, etched in symbolic language designed to be decipherable by an intelligent species with no knowledge of human conventions. Carl Sagan, who chaired the committee that designed the records, described them as a message in a bottle cast into the cosmic ocean. The gesture was romantic, hopeful, and entirely consistent with the prevailing belief that contact with alien intelligence would be one of the most magnificent events in human history for both parties involved. The dream of contact shaped not just science but the broader culture of the 20th century. Films like Close Encounters of the Third Kind portrayed aliens arriving to share music and wonder with an awestruck humanity. Contact, based on Carl Sagan's own novel, imagined extraterrestrial beings sending us the blueprints for a machine designed to bridge the unimaginable distances between civilizations. Even stories that depicted aliens as dangerous tended to frame contact as a dramatic event that humanity could ultimately survive and grow from. The dominant cultural narrative was clear and consistent. Meeting alien intelligence might be frightening, but it would also be meaningful, transformative, and ultimately worth the risk. This optimism was not naive or unexamined. It was grounded in a reasonable chain of logic that many scientists found persuasive. Any civilization capable of interstellar communication or travel must have survived long enough to develop extraordinarily advanced technology. Survival over such long time periods presumably requires a degree of cooperation, institutional stability, and the ability to manage existential risks without self-destruction. Therefore, the argument went, truly advanced civilizations would likely be wise, collaborative, and curious rather than recklessly aggressive. The very qualities that enabled them to endure and reach the stars would make them inclined toward peaceful exchange rather than conquest. Some scientists extended this reasoning further still. Astronomer Jill Tarter, one of the pioneering figures in SETI research and a lifelong advocate for the search, argued publicly that any species advanced and long-lived enough to communicate across interstellar distances would have evolved beyond the kind of territorial aggression that characterizes younger civilizations. Douglas Vakoch, president of METI International, an organization dedicated to crafting and transmitting messages to extraterrestrial intelligence, contended that the ability to interpret an interstellar message requires such sophisticated social and cognitive capacities that any civilization capable of receiving our signals would almost certainly be open to peaceful coexistence. The logic was comforting and widely accepted, and so the search continued. Decade after decade, scientists listened. Radio telescopes scanned the sky across billions of individual frequencies. Optical SETI programs searched for brief laser pulses from distant civilizations. Space telescopes catalogued thousands of exoplanets, identifying dozens of potentially habitable worlds in the so-called Goldilocks zone, the region around a star where temperatures might allow liquid water to persist on a planet's surface. The Kepler Space Telescope, launched in 2009, revolutionized our understanding of planetary abundance. It confirmed that planets are extraordinarily common throughout the galaxy. Nearly every star hosts at least one world. Rocky planets orbiting in habitable zones around sun-like stars number in the billions within the Milky Way alone. The James Webb Space Telescope, operational since 2022, has begun probing the atmospheres of some of these worlds, searching for chemical signatures that might indicate biological activity. The numbers kept improving, the opportunities for life kept multiplying. The scientific case for a populated galaxy grew stronger with every new discovery, every newly confirmed exoplanet, every refinement to our understanding of how life might arise from the raw materials that exist everywhere in the cosmos. Water is abundant, organic chemistry is universal, the building blocks of biology are not rare or exotic. They are scattered throughout interstellar space in molecular clouds, on comets, on asteroids, on the surfaces and in the subsurface oceans of moons and planets throughout our own solar system. And yet, through all of it, through more than 6 decades of listening with increasingly powerful instruments, through surveys of millions of stars across vast stretches of the electromagnetic spectrum, through careful analysis of every anomalous signal and unexplained observation, the result remained stubbornly, maddeningly, inexplicably the same. Silence. Not a single confirmed artificial signal from beyond Earth. Not one unambiguous transmission. Not a repeating pattern that resisted natural explanation. Not a whisper of technology detected among the billions of stars we have examined. The universe answered our hopeful listening with nothing, and it answered our deliberate calls with nothing either. The silence is not subtle. It is not a matter of insufficient data or limited technology. Consider what the numbers tell us. The Milky Way galaxy is approximately 13.6 billion years old. Our own solar system formed only about 4.6 billion years ago, meaning the galaxy existed for 9 billion years before Earth even coalesced from its cloud of gas and dust. Stars significantly older than our Sun had billions of additional years for life to emerge on their planets, evolve through increasing complexity, develop intelligence, build technology, and spread outward into the galaxy. Even using extraordinarily conservative estimates for the speed of interstellar colonization, traveling at a fraction of 1% of the speed of light with long pauses between settlements, a single determined civilization could have reached every habitable star system in the Milky Way within a few tens of millions of years. That sounds like a staggeringly long time from a human perspective, but it represents less than 1% of the galaxy's total age. The galaxy has had enough time for this to happen not once, not twice, but hundreds of times over. And yet, when we look at the cosmos with every instrument we possess, we see no evidence that it has ever happened. No megastructures enclosing distant stars to harvest their energy. No unmistakable chemical signatures of industrial activity on exoplanet atmospheres. No self-replicating probes arriving in our solar system. No laser beacons cutting through the electromagnetic noise. Nothing that says unambiguously, someone was here, someone built this, someone is broadcasting. This profound contradiction between the apparent probability of extraterrestrial intelligence and the total absence of evidence for it was first articulated sharply during a casual lunch conversation in the summer of 1950. A group of physicists at Los Alamos National Laboratory, including the legendary Enrico Fermi, were discussing recent UFO reports and the possibility of alien civilizations. After some calculations about the likelihood and feasibility of interstellar travel, Fermi turned to his colleagues and asked a question that has haunted science ever since. Where is everybody? The question became known as the Fermi paradox, and its deceptive simplicity conceals enormous depth. If intelligent life is even moderately common, and if even a tiny fraction of civilizations develop the desire and the capability to explore or communicate, the galaxy should be saturated with observable activity. The timescales involved are so vast and the number of potential starting points so large that even extraordinarily rare events should have produced detectable results billions of years ago. Yet we observe nothing. The paradox is not merely that we have not found aliens. It is that, given everything we know about the age, size, chemical richness, and structural organization of the galaxy, their absence demands an explanation. Something is preventing the expected outcome. Something is filtering, constraining, or silencing the civilizations that should exist. Dozens of proposed solutions have been offered over the decades since Fermi posed his question. Some are cautiously optimistic. Perhaps intelligent life is genuinely rarer than the Drake equation's hopeful inputs suggest. Perhaps the emergence of complex multicellular organisms, or the transition from simple biology to technological civilization, requires such an improbable chain of events that Earth truly is one of very few worlds where it has happened. This is the rare Earth hypothesis, and while it cannot be ruled out, the continuing discovery of potentially habitable exoplanets and the apparent universality of organic chemistry make it increasingly strained as a complete explanation for total cosmic silence. Others propose that civilizations inevitably destroy themselves before they can become spacefaring or detectable. Nuclear weapons, climate destabilization, engineered pathogens, runaway artificial intelligence, resource depletion. The list of existential threats that could extinguish a technological species is long and sobering. This is the concept of the Great Filter, a hypothetical barrier in the development of civilizations that very few, if any, manage to survive. If the filter lies in our past, perhaps in the unlikely origin of life itself or in some other bottleneck we have already passed, then we are lucky survivors of a genuinely rare event. If the filter lies ahead of us, then our future may be far shorter and darker than we imagine. Still others suggest that alien civilizations exist, but are undetectable for reasons that have nothing to do with destruction or rarity. Perhaps they communicate using methods or frequencies we have not thought to monitor. Perhaps they exist in forms so alien to our expectations that we would not recognize their technology even if we were staring directly at it, communicating through channels we have not imagined, and pursuing goals that bear no resemblance to expansion or contact. Perhaps the galaxy is quietly partitioned into spheres of influence, and our region simply happens to fall in an unoccupied frontier. Perhaps advanced civilizations are watching us but deliberately withholding contact, a scenario called the zoo hypothesis, treating Earth as a nature preserve or a long-running experiment in cultural development. Each of these explanations addresses some aspect of the paradox. None fully resolves it. The silence remains stubborn, resistant to comfortable answers, growing more conspicuous with every year of searching that finds nothing. And then there is another category of explanation entirely, one that begins not with the absence of life, but with its hidden presence. One that does not assume the galaxy is empty, but instead asks a far more unsettling question about why it appears that way. What if the galaxy is full of civilizations and they are all deliberately hiding? What if the silence is not a mystery to be solved, but a behavior to be understood? What if every advanced civilization in the Milky Way has independently learned something that humanity has not yet grasped? A strategic truth so fundamental and so terrifying that universal obedience to it is the price of continued existence. What if the quietest civilizations are not the most primitive, but the ones that have survived the longest? This question marks the boundary between the hopeful story of contact that has guided humanity for generations and something far darker. For most of its history, the search for extraterrestrial intelligence operated under a single core assumption: silence means absence. No signals meant no civilizations. The cosmos was lonely, and the solution was to keep searching, keep listening, keep sending messages outward in every direction. But a growing number of scientists, game theorists, strategic thinkers, and philosophers have begun to take seriously an alternative interpretation of the same evidence, one that turns the entire framework of the search on its head. The silence might not mean the universe is empty. The silence might mean the universe is extremely careful. Consider what humanity has already done under the assumption that broadcasting is harmless. We have sent targeted radio transmissions towards specific star systems on multiple occasions since the Arecibo message, aiming concentrated beams of encoded information at nearby sun-like stars and potentially habitable worlds. Some of these transmissions were designed to reach their targets within our lifetimes. At least one is expected to arrive at a star known to host planets in its habitable zone within the next decade. Each transmission was more sophisticated than the last, carrying richer scientific and cultural content, aimed with greater precision, and powered by transmitters whose effective radiated output dwarfed anything our planet emits accidentally by factors of millions. If anything out there possesses the technology to detect a directed signal across interstellar distances, we have given it something to find. We have done all of this without international consensus on whether broadcasting is safe. No global governing body authorized the Arecibo message. No treaty governs who can transmit signals into space on behalf of all 8 billion human beings. No risk assessment was conducted before scientists pressed the button. Small groups of researchers, driven by curiosity and guided by the assumption that the universe rewards openness, have unilaterally announced our existence and location to the cosmos without consulting the species whose survival might depend on who, if anyone, is paying attention. Not everyone shared this confidence. A small but persistent minority of scientists and strategic thinkers had been raising uncomfortable questions about the wisdom of broadcasting for decades. Their concerns were rarely given equal weight in the public conversation, partly because the optimistic narrative was so deeply embedded in the culture of the search, and partly because the objections felt abstract in the absence of any evidence that anyone was actually listening. But the objections existed, and they rested on a foundation of logic that was harder to refute than many of the search's most enthusiastic proponents were willing to admit. The questions they asked were simple enough. What if the universe does not reward openness? What if the first civilization to detect our signals does not share our assumption that contact is desirable? What if the silence itself is not a gap in the data, but the data? But these warnings have largely been treated as the anxieties of pessimists in a field built on hope. The search for contact has always been fueled by the conviction that the universe is fundamentally a place where connection is possible, and discovery is inherently good. The default assumption has been that any civilization advanced enough to detect our signals would be advanced enough to be peaceful. What if that assumption is not just wrong, but the single most dangerous idea that any young civilization can hold? Because there is a theory that takes the Fermi paradox, the silence of the cosmos, the mathematics of survival, and the logic of strategic uncertainty, and assembles them into one coherent and deeply disturbing conclusion. A theory that does not require aliens to be evil or predatory. A theory that does not depend on science fiction or paranoid speculation. A theory constructed entirely from game theory, the physics of cosmic distance, and the cold algebra of survival in a universe where trust is impossible and ignorance is lethal. It is called the dark forest theory, and what it says about the meaning of cosmic silence will fundamentally change how you interpret every signal humanity has ever sent into the sky. The theory did not originate in a scientific journal or a university lecture hall. It emerged from a work of fiction, which is part of what makes it so easy to dismiss and so difficult to forget. In 2008, Chinese science fiction author Liu Cixin published a novel called The Dark Forest, the second volume of his Remembrance of Earth's Past trilogy. The book introduced a concept that escaped its fictional context almost immediately and entered serious scientific and philosophical discourse, where it has remained ever since. The concept was framed as a discovery made by a character named Luo Ji, who derives the logic of cosmic survival from a handful of axioms the way a mathematician might derive theorems from first principles. The reasoning is airtight within its assumptions. The conclusion is devastating. And the most unsettling thing about it is that the logic does not depend on aliens being cruel. It depends only on them being rational. But before examining the theory itself, it is important to understand that while Liu Cixin gave the idea its most complete and famous articulation, the underlying reasoning has appeared in various forms throughout the history of thinking about extraterrestrial life. Astronomer and science fiction author David Brin explored similar concepts in his 1983 survey of arguments surrounding the Fermi paradox, describing scenarios in which advanced civilizations might systematically eliminate emerging species to prevent future competition. The idea of deadly probes, self-replicating machines dispatched to sterilize any star system showing signs of technological development appeared in Brin's work and in other speculative analyses of interstellar conflict. Science fiction author Greg Bear, in his 1987 novel The Forge of God, depicted humanity as a baby crying in a hostile forest, drawing down wolves with every signal it emits. These ideas were not taken particularly seriously by mainstream science at the time. They were treated as interesting thought experiments, the kind of dark scenarios that science fiction is uniquely suited to explore, but that real-world scientists could safely set aside in favor of more optimistic frameworks. The dark forest theory changed that calculation, not because Liu Cixin had access to information other authors lacked, but because his formulation distilled the logic into something so clean, so minimal in its assumptions, and so resistant to comfortable counterarguments that it demanded engagement even from researchers who found its conclusion repellent. The theory begins with two axioms. These are not exotic or controversial. They are, in fact, so reasonable that almost any biologist, economist, or evolutionary theorist would accept them without argument. The first axiom states that survival is the primary need of every civilization. This does not mean that civilizations care only about survival. It means that survival is the prerequisite for everything else. A civilization that ceases to exist cannot pursue knowledge, create art, build relationships, or fulfill any other purpose. Whatever a civilization values, it must first continue to exist in order to value it. This is not a statement about aggression or hostility. It is a statement about priorities. Every organism, every species, every society that has ever existed on Earth has operated under this principle, consciously or not. The drive to persist is the foundation upon which all other drives are built. The second axiom states that civilizations continuously grow and expand, but the total matter and energy in the universe remains constant. Again, this is not controversial. It is an observation drawn from thermodynamics and from the history of every civilization humans have ever studied. Populations grow, resource consumption increases, territorial requirements expand. This does not mean that every civilization expands aggressively, or that expansion necessarily takes the form of military conquest. It simply means that over sufficiently long time periods, a growing civilization will require more resources than its immediate environment provides. And the universe, despite its staggering size, contains a finite amount of matter and energy distributed across a finite, though enormous, number of star systems. These two axioms alone do not produce the dark forest conclusion. If the universe were small and fully transparent, civilizations could observe each other, assess intentions, negotiate agreements, and build cooperative relationships much as nations on Earth have done, imperfectly and often violently, but with at least some capacity for diplomacy and mutual understanding. The critical ingredients that transform these reasonable axioms into a terrifying conclusion are two additional concepts that Liu Cixin introduced as the chain of suspicion and the technological explosion. The chain of suspicion is the more immediately intuitive of the two, and it is rooted in a problem that game theorists and political scientists have studied for decades on Earth, though never before at cosmic scale. The problem is this: when two civilizations become aware of each other's existence across interstellar distances, neither can reliably determine the other's intentions. This is not merely a technical limitation that better technology could resolve. It is a structural feature of the situation itself, arising from the combination of distance, communication delay, and the fundamental opacity of alien minds. Consider what happens when Civilization A detects evidence of Civilization B. The first question A must ask is whether B is hostile or peaceful. On Earth, when two human nations encounter each other for the first time, they can observe behavior, exchange ambassadors, establish trade relationships, and gradually build a foundation of trust, or at least of mutual understanding. This process is imperfect and frequently fails, as the long history of warfare demonstrates. But it is at least possible because human nations share a common biology, occupy the same planet, and can communicate with relatively short delays. Messages can be sent and received within days or hours. Ambassadors can travel between capitals within weeks. Behavior can be monitored continuously. Agreements can be enforced, or at least their violation can be detected quickly enough to allow a response. None of these conditions hold at interstellar scale. The nearest star to our Sun, Proxima Centauri, is approximately 4.2 light-years away. A radio message sent to a civilization orbiting that star would take over 4 years to arrive. A reply would take another 4 years. A single exchange of greetings would consume nearly a decade. A meaningful negotiation involving multiple rounds of communication could stretch across centuries, and Proxima Centauri is the closest possible neighbour. Most stars in the galaxy are separated by distances of tens, hundreds, or thousands of light-years. Communication with a civilization on the far side of the Milky Way would require 100,000 years for a single message to arrive. Under these conditions, the normal process of trust building that civilizations use to manage relations with unknown neighbours becomes functionally impossible. You cannot assess another civilization's character through dialogue when each exchange takes decades or centuries. You cannot monitor their behavior in real time when the light showing you their current state left their world before your grandparents were born. You cannot enforce agreements when violations would not be detected for generations. The infrastructure of trust that makes coexistence possible between human nations, imperfect as it is, simply does not exist at interstellar distances. It cannot be built. The physics of the situation forbids it, but the chain of suspicion goes deeper than the practical difficulty of communication. Even if two civilizations could somehow establish rapid contact, they would face a more fundamental problem. Neither civilization can ever be certain of the other's true nature. Not just their current intentions, but their deepest motivations, their evolutionary psychology, their capacity for deception, and their future trajectory. When two human nations interact, they share enough biological and cultural common ground that intentions can be at least partially inferred. Facial expressions, body language, historical precedent, economic incentives, political structures, all of these provide information, however imperfect, about what the other party is likely to do. Between alien civilizations separated by light years and potentially billions of years of independent evolution, no such common ground exists. The other civilization might think in ways that have no analogue in human experience. Its concept of communication, cooperation, threat, promise, and agreement might be so different from ours that mutual understanding is not merely difficult but genuinely impossible. This is where the chain of suspicion becomes recursive. Civilization A does not know whether civilization B is hostile. But even if A assumes B is peaceful, A cannot know whether B believes A is peaceful. And even if both A and B are genuinely peaceful, A cannot know that B knows that A knows that B is peaceful. The uncertainty propagates infinitely. Each level of inference adds another layer of doubt. This infinite regression of mutual uncertainty is the chain of suspicion, and it cannot be broken by any finite number of messages, promises, or demonstrations of goodwill. On Earth, we manage these recursive uncertainties through institutions, repeated interactions, and shared frameworks of meaning. International law, trade agreements, cultural exchange, diplomatic norms, these are all mechanisms for collapsing chains of suspicion into manageable levels of uncertainty. But every single one of these mechanisms depends on proximity, speed of communication, shared context, and the ability to verify and enforce agreements. Remove all of those conditions, as interstellar distance does, and the chain of suspicion becomes unbreakable. A civilization facing this chain has a limited set of options. It can attempt communication and hope that the other party responds peacefully, accepting the risk that it might not. It can remain silent and hope that it has not already been detected, or it can take preemptive action to eliminate the potential threat before the other civilization has a chance to act. Each of these options carries enormous risk, but the chain of suspicion ensures that none of them can be pursued with confidence, and it creates a persistent, irreducible anxiety that shapes all strategic thinking about interstellar relations. The second concept, the technological explosion, makes this anxiety unbearable. On Earth, technological development has accelerated at rates that would have been unimaginable to earlier generations. 200 years ago, the fastest means of communication was a horse-drawn courier. 100 years ago, radio was a novelty. 50 years ago, computers filled entire rooms and had less processing power than a modern wristwatch. 20 years ago, smartphones did not exist. The interval between major technological revolutions has been shrinking consistently, and each revolution has brought capabilities that the previous generation could not have predicted. Now extend this observation to cosmic timescales. A civilization that is technologically primitive today, perhaps still in its equivalent of Earth's industrial age, could undergo a technological explosion and develop interstellar travel, planet-destroying weapons, or self-replicating war machines within a few centuries. A few centuries is nothing in cosmic terms. It is a rounding error in the life of a star, an eye blink in the history of a galaxy. This means that no civilization, however advanced, can safely assume that a less developed neighbour will remain harmless. The gap between primitive and dangerous can close within a time period so short that it barely registers on astronomical timescales. This is the nightmare that the technological explosion introduces into the strategic calculus of the dark forest. It is not enough to assess whether another civilization is currently dangerous. You must assess whether it could become dangerous within a cosmically insignificant period, and the answer is almost always yes. Human history alone demonstrates the point. In 1900, powered flight did not exist. By 1969, humans had walked on the moon. By the late 20th century, humanity possessed nuclear arsenals capable of rendering the planet uninhabitable. From the perspective of any civilization watching from a distance of even a few hundred light years, Earth transitioned from harmless to potentially lethal in a span of time shorter than the round-trip communication delay between nearby stars. Combine the chain of suspicion with the technological explosion, and the strategic landscape becomes extraordinarily bleak. You have detected another civilization. You cannot determine its intentions. You cannot communicate with it fast enough to build trust. Even if it appears harmless now, you know that technological development could transform it into an existential threat within a few centuries, a period too short for you to monitor and respond to in time. You cannot verify any promise it makes. You cannot enforce any agreement you might reach. And you know that the other civilization is performing exactly the same calculation about you. This is the game theoretic structure that the dark forest theory identifies as the fundamental condition of interstellar relations. It resembles the prisoner's dilemma, one of the most studied problems in game theory, but with several features that make it far worse than any terrestrial version of the problem. In the classic prisoner's dilemma, two players each choose whether to cooperate or defect, without knowing the other's choice. If both cooperate, both benefit. If one cooperates while the other defects, the cooperator suffers a devastating loss while the defector gains enormously. If both defect, both suffer, but less than the cooperator who is betrayed. In repeated versions of the dilemma, where the same players interact many times, cooperative strategies can emerge because players learn to reciprocate cooperation and punish defection. Tit-for-tat strategies, where you cooperate first and then mirror the other player's most recent move, have been shown to be remarkably effective in promoting cooperation over time. But the cosmic version of this dilemma has features that prevent cooperation from emerging through any known mechanism. First, the interactions are not repeated. Given the vast distances and communication delays involved, a civilization might get only one chance to act before the consequences become irreversible. There is no opportunity for the iterative trust building that makes cooperation rational in repeated games. Second, the stakes are existential. In a standard prisoner's dilemma, the payoffs are finite and recoverable. A player who is betrayed can survive and adjust their strategy for the next round. In the cosmic version, the cost of being wrong is civilizational annihilation. There is no next round for a civilization that trusted incorrectly. Third, and most crucially, there is no enforcement mechanism. On Earth, legal systems, international institutions, and the threat of collective punishment provide at least some deterrent against betrayal. In the cosmos, no such institutions exist. Agreements between civilizations separated by thousands of light years cannot be monitored, verified, or enforced by any mechanism currently known to physics, or plausibly extrapolated from it. Each civilization operates in a strategic vacuum, making decisions with existential consequences based entirely on its own assessment of a situation it can never fully observe. Under these constraints, the game theoretic equilibrium is grim. The only strategy that reliably ensures survival is the one that does not require trust. Remain hidden, and if you detect another civilization before it detects you, eliminate it before it can pose a threat. Not because you are evil, not because you enjoy destruction, not because you have assessed the other civilization and determined it to be hostile, but because the structure of the situation makes any other choice a gamble with your civilization's existence, and the expected cost of losing that gamble is infinite. To understand why this logic feels so inescapable, it helps to walk through the decision tree that a civilization faces step by step, stripping away abstraction and forcing each choice into concrete terms. Imagine that your civilization has just detected unmistakable evidence of another technological species. Perhaps you intercepted a targeted radio transmission, a narrowband signal carrying encoded information from a star system 80 light-years away. The signal is unambiguously artificial. There is no natural process that could produce it. You now know, with certainty, that another civilization exists, and you know approximately where it is located. The question is, what to do with this knowledge? Your first option is to respond. You could transmit a message back, introducing yourself, sharing scientific knowledge, proposing peaceful exchange. This is the option that feels most natural to a species like humanity, raised on stories of contact and cooperation. But consider what responding actually costs you. By transmitting a reply, you confirm your own existence and reveal your own location to the civilization that sent the original signal. You also reveal your location to every other civilization within range of your reply, civilizations you may not know about, and whose existence the original senders may not know about either. Your reply does not travel only to its intended recipient. It radiates outward in all directions, announcing your position to the entire surrounding volume of space. And you have no way of knowing who else is listening. Furthermore, your reply will not arrive at its destination for 80 years. A response to your reply will not reach you for another 80 years. A single exchange of greetings consumes 160 years. Meaningful negotiation would require multiple exchanges spanning centuries or millennia. During that entire period, you know nothing about how the other civilization is developing, what strategic decisions it is making, or whether its intentions toward you have changed. You are conducting diplomacy across a communication gap so vast that entire political systems could rise and collapse between messages. Your second option is to remain silent and observe. You could watch the other civilization from a distance, gathering information without revealing yourself. This is safer than responding, but it introduces its own risks. You do not know whether the other civilization has already detected you through your own leaked emissions or previous transmissions. You do not know whether a third civilization has also detected both of you and is making its own calculations. And you are aware that every year you spend observing is a year in which the other civilization continues to develop technologically. If it is currently less advanced than you, this gap may close. If it is currently more advanced, you learn nothing from observation that would help you in a confrontation. Time does not necessarily work in your favor. Your third option is to attempt preemptive action, to neutralize the other civilization before it can pose a threat. This is the option that most people instinctively recoil from, and understandably so. It requires destroying an entire civilization based on the mere possibility that it might someday become dangerous, not on evidence that it has hostile intentions, not on any act of aggression, but purely on the logic that you cannot afford to be wrong. It is, by any human moral standard, monstrous. And yet the dark forest theory argues that the structure of the situation makes it the only option that does not require gambling your civilization's existence on assumptions you cannot verify. Notice what has happened in this decision tree. Every path that involves communication, cooperation, or trust requires you to make assumptions about the other civilization's nature and intentions that you have no way of verifying. Every path that involves patience and observation requires you to accept increasing risk as the other civilization develops. Only the path that eliminates the unknown variable removes the uncertainty entirely. The logic does not reward openness. It does not reward curiosity. It does not reward the qualities that humanity considers its highest virtues. It rewards only the willingness to act decisively on incomplete information in a situation where the cost of hesitation might be measured in billions of lives. The gut response to this reasoning is to reject it on moral grounds, and that response is valid as a statement of values. But the dark forest theory is not making a moral argument, it is making a strategic one. It is describing what rational actors will do under specific conditions, not what they should do according to any ethical framework. The distinction matters because the theory does not require every civilization to embrace the logic enthusiastically. It requires only that enough civilizations act on it to make the cosmos dangerous for those that do not. A single predatory civilization in a galaxy of pacifists is enough to make silence the dominant survival strategy for everyone. You do not need a forest full of wolves. You need only one wolf and the knowledge that wolves exist. There is a terrestrial parallel that illuminates both the power and the limits of this reasoning, and it comes from the most dangerous strategic standoff in human history. During the Cold War, the United States and the Soviet Union developed nuclear arsenals capable of destroying each other and much of the planet multiple times over. The strategic doctrine that governed this standoff was mutually assured destruction, the recognition that any nuclear first strike would be met with a retaliatory strike of equal or greater magnitude, ensuring that neither side could win a nuclear war. This mutual vulnerability created a perverse form of stability. Both sides refrained from attacking not because they trusted each other, but because the consequences of attacking were unacceptable regardless of the outcome. Mutually assured destruction worked, imperfectly and terrifyingly, because several critical conditions were met. Both sides could verify each other's capabilities through satellite reconnaissance and intelligence gathering. Communication between Moscow and Washington was possible within minutes through hotline agreements. The geographic proximity of the two superpowers meant that the consequences of a first strike would be felt almost immediately, within 30 minutes for intercontinental ballistic missiles, leaving no time for the strategic landscape to shift between the decision to attack and the arrival of retaliation. And both sides were composed of human beings with shared biological imperatives and at least partially overlapping cultural frameworks, making each side's reasoning about the other's behavior at least approximately predictable. Now remove every single one of these conditions. Replace minutes of communication delay with decades or centuries. Replace verifiable capabilities with total opacity. Replace geographic proximity with distances measured in light years. Replace shared biology and cultural frameworks with minds shaped by billions of years of independent evolution on alien worlds. Replace the 30-minute flight time of a nuclear missile with the centuries or millennia required for any physical interaction between star systems. What remains is a strategic environment in which mutually assured destruction cannot function. Deterrence requires that your adversary knows you can retaliate and believes you will. Across interstellar distances, neither condition can be reliably established. Your adversary may not know where you are. You may not know where they are. A retaliatory strike launched across 80 light-years would not arrive for centuries, by which time the attacking civilization could have relocated, fortified, or developed defenses against whatever you sent. The feedback loop that makes deterrence stable on Earth, the knowledge that aggression will be met with immediate and devastating consequences, simply does not close at interstellar scales. The delay is too long. The uncertainty is too great. The ability to verify, communicate, and enforce is too weak. This is why the Cold War parallel, while instructive, ultimately demonstrates the opposite of what people might initially expect. It does not show that civilizations can manage the dark forest through deterrence. It shows that deterrence depends on conditions that the cosmos does not provide. The same logic that prevented nuclear war between two nations on the same planet breaks down completely when applied to civilizations separated by the vast, silent distances between stars. The strategic environment of the cosmos is not analogous to the Cold War. It is analogous to a world in which nuclear-armed states cannot see each other, cannot talk to each other, cannot verify each other's arsenals, and cannot retaliate within any meaningful time frame. In such a world, the logic of preemptive action becomes far more compelling, and the logic of deterrence becomes far less reliable. This is the dark forest. The metaphor is precise and deliberate. Imagine a vast dark forest at night. You are a hunter moving through the trees. You know that other hunters are out there, but you cannot see them. You do not know how many there are, where they are, or what weapons they carry. You do not know whether they are friendly or hostile. You cannot call out to ask, because the sound of your voice would reveal your position to every hunter in the forest. Some of those hunters might be friendly. Some might be willing to cooperate. But some might shoot at any sound they hear, and you have no way of telling which is which before you reveal yourself. The rational strategy, the one that maximizes your chances of surviving the night, is to move silently, remain invisible, and if you spot another hunter before they spot you, make a decision about what to do while you still have the advantage of surprise. Now scale this metaphor to a galaxy containing billions of stars, potentially millions of civilizations, and timescales measured in billions of years. The forest is not a few square miles of woodland. It is 100,000 light-years across. The hunters are not individuals who will go home at dawn. They are civilizations that endure for millennia or longer, and for whom the stakes of detection are not personal survival but the survival of entire species, entire biospheres, entire histories of art, science, culture, and consciousness. In this forest, every civilization faces the same strategic dilemma. Broadcasting your position is dangerous because it reveals your location to every other civilization within range of your signal. Some of those civilizations may be benign, but you cannot determine which ones, and you cannot afford to be wrong. The cost of being wrong is not embarrassment or economic loss, it is extinction. And extinction is permanent. There are no second chances. The theory predicts a specific behavior that should be observable if the logic is correct. Universal silence. Every civilization that has survived long enough to understand the strategic landscape of the cosmos will independently converge on the same conclusion. Hide. Do not transmit. Do not respond to signals from others. If you detect a civilization that has revealed its position, you face a choice, one that the theory suggests may have only one survivable answer. Because if you do not act on the knowledge of another civilization's location, someone else in the forest might. And if that someone else eliminates the revealed civilization and then detects your own position through your failure to act, you become the next target. This cascading logic creates what might be called an ecosystem of silence. It is not that one tyrannical civilization enforces quiet on the rest. It is that the structure of the game itself selects for quiet. Civilizations that broadcast are exposed. Civilizations that remain hidden persist. Over billions of years, the galaxy becomes populated overwhelmingly by civilizations that have learned, through logic or through the example of others who learned too late, that the first rule of cosmic survival is to never let anyone know you exist. There is an important distinction to draw here between what the dark forest theory claims and what it does not. The theory does not claim that all alien civilizations are hostile. It does not require a universe populated by psychopathic predators roaming the stars in search of victims. Hostility is not the engine of the dark forest. Uncertainty is the engine. The theory requires only that some fraction of civilizations, even a very small fraction, might be hostile or might become hostile in the future. Given the impossibility of determining which civilizations fall into that category and the permanent, irreversible consequences of guessing wrong, the rational response is to treat every unknown civilization as a potential threat. This is the chilling insight that separates the dark forest theory from simple alien invasion narratives. The engine driving this outcome is not malice, but mathematics. The theory functions identically whether the civilizations involved are aggressive empires or peaceful scientists. Their moral character is irrelevant to the strategic calculus. What matters is that they are rational enough to recognize the constraints they operate under and cautious enough to act accordingly. Distance makes communication impractical. The chain of suspicion makes trust impossible. The technological explosion makes even weak civilizations potentially dangerous. And the absence of any enforcement mechanism means that cooperation cannot be guaranteed even between parties that genuinely desire it. The theory also carries a disturbing implication about what cosmic silence tells us. Under the dark forest framework, the Fermi paradox is not a mystery. It is a confirmation. The reason we hear nothing is not that civilizations are rare. It is not that they self-destruct before reaching technological maturity. It is not that they are hiding in some exotic post-biological form that we cannot detect. It is that they are deliberately silent because they have understood something that humanity has not yet fully grasped. They have learned the rules of the forest. And the first rule, the rule that every surviving civilization has internalized so deeply that it shapes every aspect of their relationship with the cosmos, is this: do not make a sound. What makes this theory so uniquely disturbing among Fermi paradox solutions is not its pessimism, but its internal consistency. Most explanations for cosmic silence require some assumption that is speculative or difficult to verify. The rare Earth hypothesis requires that the emergence of complex life involves improbable bottlenecks we have not yet identified. The Great Filter requires a catastrophic barrier that we cannot yet observe. The zoo hypothesis requires a coordinated decision by all advanced civilizations to leave us alone, which raises its own coordination problems. The dark forest theory requires only the axioms it begins with, and the game theoretic reasoning that follows from them. Every step in the chain is defensible, every assumption is conservative, and the conclusion, while horrifying, is logically coherent. This does not mean the theory is correct. It means it cannot be dismissed with the comfortable assurance that the universe is too big, too old, or too full of potential for something so dark to be true. The very features of the cosmos that make contact seem likely, the vastness, the age, the abundance of stars and planets, are the same features that make the dark forest logic operational. A universe with trillions of planets and billions of years of evolutionary history is precisely the kind of universe where strategic uncertainty becomes unmanageable, where trust cannot scale across the distances involved, and where the safest survival strategy may indeed be to remain invisible. The theory sits at the intersection of cosmology, evolutionary biology, and game theory. It draws on our understanding of how competition for finite resources shapes behavior in biological systems. It uses the mathematics of strategic interaction under uncertainty to predict what rational actors will do when the stakes are existential and the information environment is permanently opaque. And it applies these tools not to the behavior of individual organisms or competing firms, but to the behavior of entire civilizations spanning thousands of years and thousands of light years. And it raises a question that is no longer theoretical for humanity, because we have already done something that, under dark forest logic, might be the most dangerous act our species has ever performed. We have announced our existence, we have broadcast our location, we have sent targeted, high-powered radio transmissions towards specific star systems, transmissions designed to be detected, decoded, and traced back to their origin. Under the assumptions of the dark forest, every one of those signals is a flare fired in the middle of a dark forest full of armed and watchful hunters. The question is no longer whether the logic of the dark forest makes theoretical sense. The question is what it means that we have already ignored it, and what the consequences might be if the universe operates according to its rules. There is a difference between a theory that disturbs you in the abstract and one that implicates something you have already done. The dark forest theory crosses that line the moment you realize that humanity has not merely contemplated sending signals into space. We have sent them, repeatedly, deliberately, with increasing power and precision, and in most cases, without the knowledge or consent of the vast majority of the species whose survival might depend on whether anyone out there is paying attention. Understanding the true scope of what humanity has transmitted requires distinguishing between two fundamentally different categories of electromagnetic emission. The first is passive leakage, the unintentional radio signals that have been radiating outward from Earth since the early 20th century. The second is active transmission, the deliberate, targeted, high-powered signals designed specifically to be detected by extraterrestrial intelligence. The difference between these two categories is not merely technical. Under dark forest logic, it is the difference between a faint rustling in the underbrush and a sustained shout echoing across the forest. Passive leakage began roughly a century ago when commercial radio broadcasting emerged in the 1920s. Since then, Earth has been radiating electromagnetic energy in all directions, from radio transmitters, television stations, military radar installations, satellite communication systems, and an ever-growing array of digital communication technologies. This expanding sphere of radio emissions, sometimes called Earth's radio bubble, now extends outward approximately 100 light-years from our planet. In principle, any civilization within that radius with sufficiently sensitive receiving equipment could detect anomalous electromagnetic emissions coming from the direction of our Sun. This fact has led to what is commonly called the barn door argument, one of the most frequently cited justifications for active messaging programs. The argument is straightforward. The barn door is already open. We have been leaking signals for a century. Any sufficiently advanced civilization within 100 light years already knows we are here. Therefore, there is no additional risk in sending deliberate, targeted transmissions. We cannot hide, so we might as well speak clearly. The barn door argument is intuitive, widely repeated, and, according to a significant number of scientists who have studied the question carefully, dangerously wrong. The problem with the argument lies in the physics of signal propagation across interstellar distances. Electromagnetic signals weaken according to the inverse square law. Every time the distance from the source doubles, the signal strength drops to 1/4. This means that Earth's leaked radio and television signals, which were never designed for interstellar communication, become extraordinarily faint within a remarkably short distance from our planet. The power output of a typical commercial radio station is measured in kilowatts, occasionally reaching hundreds of kilowatts for the most powerful stations. Military radar installations are more powerful, sometimes reaching megawatts of peak power, but they are not omnidirectional and they operate intermittently. By the time these signals have travelled even a few light years, they have spread across such an enormous volume of space that their energy density drops to levels far below the natural electromagnetic background noise of the galaxy. Cosmic radio sources, including pulsars, quasars, synchrotron radiation from stellar magnetic fields, and the ever-present hiss of the cosmic microwave background, all contribute to a noisy electromagnetic environment in which faint, diffuse signals from a single planet quickly become undetectable. Scientists have calculated what it would take for an alien civilization to detect Earth's leaked radio emissions from various distances. At a distance of just a few hundred light years, detecting a signal equivalent to a typical television broadcast would require a receiving antenna with a collecting area measured in thousands of square kilometers. That is not physically impossible, but it represents an engineering commitment that no civilization would undertake unless it already had strong reason to believe a signal was there. At distances of a few thousand light years, the required antenna sizes become absurd, exceeding the surface area of entire planets. At galactic distances, Earth's leaked emissions are completely indistinguishable from the natural background. They might as well not exist. Furthermore, the nature of Earth's leaked signals has changed over the decades in ways that actually make us harder, not easier, to detect. Early television and radio broadcasts used high-power analog transmissions that radiated significant energy into space. But modern communication technologies have shifted overwhelmingly toward digital formats, fiber optic cables, low-power cellular networks, and directional satellite transmissions. Each of these technologies is either non-radiating, like fiber optics, or produces signals that are far weaker and more diffuse than the analog broadcasts they replaced. Earth is actually becoming quieter as our technology advances. The radio bubble is not growing louder, it is fading. This is the critical flaw in the barn door argument. Earth's passive leakage is not a shout that has already revealed our position to the galaxy. It is a whisper that becomes inaudible within a cosmically insignificant distance. The barn door may have opened a crack, but the light escaping through that crack is so faint that it illuminates almost nothing in the vast darkness beyond. Deliberate transmissions are an entirely different matter. The Arecibo message, transmitted in 1974, used the full power of the Arecibo telescope's transmitter, approximately 450 kilowatts, focused into a narrow beam aimed at a specific target. The effective radiated power in the direction of that beam was on the order of trillions of watts, millions of times more powerful than a typical television broadcast. This enormous disparity between leaked signals and targeted transmissions is not a minor detail. It is the entire point. A directed, high-power transmission is designed to be detectable across interstellar distances. That is its explicit purpose. Comparing it to Earth's passive leakage is like comparing a military searchlight to the glow of a firefly. The cosmic call transmissions of 1999 and 2003 used similar principles. Transmitted from the Yevpatoria planetary radar in Crimea, These messages were aimed at multiple sun-like stars within approximately 70 light-years of Earth. The Yevpatoria radar, originally built for planetary research and as part of the Soviet ballistic missile warning system, produced a transmission power of approximately 150 kilowatts. When focused into a narrow beam and directed at specific stars, the effective radiated power was billions of watts, orders of magnitude above anything that Earth's leaked emissions produce. In 2017, METI International transmitted a message from the EISCAT facility in Tromsø, Norway, targeted at Luton's star, a red dwarf approximately 12.4 light-years from Earth. The signal was deliberately designed to be detectable by a civilization with technology comparable to our own, assuming they were listening in the right direction at the right frequency. Luton's star is known to host at least 2 exoplanets, one of which orbits within the star's habitable zone. The transmission will arrive at its destination in the early 2030 years. Each of these transmissions represents a qualitative escalation beyond passive leakage. They are not accidental emissions that happen to escape our atmosphere. They are concentrated beams of energy carrying encoded information, pointed at specific targets and intended to announce our existence and location to anyone capable of receiving them. Under the logic of the dark forest, each one is a precisely aimed signal flare launched into the night, and the debate surrounding these transmissions has been far more contentious than most people realize. David Brin, an astrophysicist whose early work on the Fermi paradox helped establish the intellectual framework that the dark forest theory later built upon, has been one of the most vocal and persistent critics of active messaging programs. Brin has argued for decades that no individual scientist, no small organization, and no single nation should have the authority to transmit powerful signals on behalf of the entire human species without some form of broad international consultation and consent. His objection is not that contact with extraterrestrial intelligence is impossible, or that all aliens are necessarily hostile. His objection is that the decision to announce humanity's existence and location to the cosmos is irreversible and carries consequences that would affect every person on Earth, and therefore it should not be made unilaterally by small groups of enthusiasts operating without oversight. Brin has specifically challenged the rationalizations offered by proponents of active messaging. He has debunked the barn door argument by pointing to the physics of signal attenuation described above. He has questioned the assumption that advanced civilizations would necessarily be peaceful by noting that the history of life on Earth, the only dataset we have, shows no consistent correlation between intelligence and benevolence. Dolphins are intelligent and generally peaceful. Chimpanzees are intelligent and frequently violent. Humans are the most intelligent species on the planet and have committed atrocities against each other and against the natural world on scales that beggar imagination. Intelligence alone does not predict behavior, and extrapolating from one planet's evolutionary history to make universal claims about the temperament of alien minds is not science, it is wishful thinking. The late Stephen Hawking made similar arguments from an even more prominent public platform. In a 2010 episode of his television series Into the Universe, Hawking drew an explicit parallel between potential alien contact and the European colonization of the Americas. He noted that when technologically advanced civilizations have encountered less developed ones on Earth, the outcome has almost always been catastrophic for the weaker party. The indigenous peoples of the Americas, Australia, Africa, and the Pacific Islands were not destroyed because the European colonizers were uniquely evil. They were destroyed because the power imbalance was so extreme that the colonizers' intentions, whether benign, indifferent, or actively malicious, mattered far less than their capabilities. Hawking argued that any alien civilization capable of traveling to Earth or communicating across interstellar distances would possess technology so far beyond our current capabilities that we would have no way of defending ourselves. Against hostile intentions and no reliable way of distinguishing hostile intentions from benign ones, he supported the SETI program's mission to listen for signals from extraterrestrial intelligence, but explicitly warned against transmitting, arguing that announcing our existence to the cosmos without understanding who might be listening was reckless beyond measure. These warnings have been met with significant pushback from within the scientific community. METI proponents argue that the potential benefits of contact with an advanced civilization, access to knowledge, technology, and perhaps solutions to existential problems like climate change or asteroid impacts, outweigh the speculative risks. Seth Shostak, senior astronomer at the SETI Institute, has publicly described fears about alien hostility as irrational, arguing that any civilization capable of interstellar action would have no conceivable motivation to harm a species as technologically primitive as humanity. Douglas Vakoch has argued that passive SETI itself is an implicit endorsement of active messaging, since detecting an alien signal would inevitably provoke a chaotic burst of responses from Earth, making any attempt to control our electromagnetic profile ultimately futile. But these counter-arguments, however reasonable they sound in isolation, do not actually address the core logic of the dark forest theory. The theory does not claim that aliens are definitely hostile. It claims that you cannot know whether they are hostile, and that this uncertainty itself is the danger. The theory does not require aliens to have a motivation for harming humanity. It requires only that the structure of the strategic situation makes silence the dominant survival strategy for any civilization operating under the constraints of cosmic distance, communication delay, and mutual opacity. Arguing that aliens would have no reason to harm us assumes a level of insight into alien psychology that the chain of suspicion explicitly identifies as impossible to achieve. There is another dimension to the risk of visibility that extends beyond the binary question of whether an alien civilization would choose to attack or ignore us. The dark forest theory describes a universe in which information itself is dangerous, not because of what the information contains, but because of what it reveals about the sender. A signal transmitted from Earth toward a distant star carries more than just the encoded message. It carries metadata. The frequency, bandwidth, modulation, and power level of the signal provide information about our level of technological development. The content, if it includes scientific or mathematical information as many proposed messages do, reveals the state of our knowledge. The direction and timing of the signal reveal our location with precision that increases as multiple transmissions allow triangulation. Even the decision to transmit at all reveals something strategically significant: that we are a civilization naive enough or confident enough to believe that announcing our presence carries acceptable risk. Under the chain of suspicion, this last piece of information might be the most dangerous of all. A civilization that broadcasts openly is either too primitive to understand the danger or so powerful that it does not fear discovery. Either assessment changes the strategic calculus for any civilization that detects the signal. Consider the problem from the perspective of a civilization that receives a signal from Earth. They now know several things with certainty. They know that a technological civilization exists at a specific location in the galaxy. They know approximately how advanced that civilization is based on the nature of the signal. They know that this civilization is willing to reveal itself, which means it either has not considered the possibility that visibility is dangerous, or has considered it and decided to broadcast anyway. In the first case, the broadcasting civilization is naive, which makes it vulnerable. In the second case, it is confident, which makes it potentially threatening. In neither case does the signal provide reliable information about intentions, because any civilization that wanted to appear peaceful could easily craft a message designed to convey exactly that impression regardless of its actual disposition. This is the signaling problem that game theorists recognize as fundamentally insoluble under the conditions the dark forest describes. In game theory, a signal is informative only if it is costly to fake. On Earth, diplomatic signals like troop withdrawals or arms reductions carry some weight because they impose real costs on the signaling party, though even these are frequently used deceptively. In the cosmic context, a message professing peaceful intentions costs nothing to produce and is trivially easy for a hostile civilization to imitate. There is no way for a receiving civilization to distinguish a genuine peace signal from a deceptive one. The signal collapses into what game theorists call a pooling equilibrium, a situation where all types of sender produce the same signal, making the signal informationally worthless. The result is that transmitting a message into space, no matter how carefully crafted, cannot reduce the strategic uncertainty that drives the dark forest logic. It can only increase the danger to the sender by confirming their existence and location. The message accomplishes the opposite of its intended purpose. Instead of building trust, it provides targeting information. This analysis reveals why the debate between METI advocates and their critics is not merely a disagreement about probabilities, it is a disagreement about the fundamental nature of strategic interaction under extreme uncertainty. METI proponents operate within a framework where communication is inherently beneficial, where more information leads to better outcomes, and where the default assumption should be that contact is desirable. Dark forest reasoning operates within a framework where information is inherently dangerous, where revealing your position is the costliest possible strategic error, and where the default assumption should be that any unknown civilization represents a potential existential threat until proven otherwise, proof that can never actually be obtained. The implications extend beyond deliberate messaging to encompass any activity that makes Earth more detectable. Technosignatures, the observable indicators of a technologically active civilization, include not just radio emissions but also atmospheric chemical signatures, artificial light visible from space, megastructures that alter a star's light curve, and even the gravitational effects of large-scale engineering projects. As humanity's technological footprint grows, the number and strength of our technosignatures increase. The James Webb Space Telescope is already capable of analyzing the atmospheric composition of exoplanets, searching for gases like oxygen, methane, and dimethyl sulfide that might indicate biological or technological activity. If we can do this with our current technology, a civilization even modestly more advanced than ours could do it far more effectively, scanning millions of stars for the chemical fingerprints of inhabited worlds. Under dark forest logic, this capability transforms every detectable technosignature into a liability. It is not just our radio transmissions that could betray us. The very composition of our atmosphere, altered by billions of years of biological activity and 2 centuries of industrial emissions, is a beacon that any sufficiently advanced civilization could detect. The chlorofluorocarbons, nitrogen dioxide, and other industrial pollutants in our atmosphere are markers of technology that do not occur naturally. They are, in effect, involuntary signals that we cannot turn off. This creates a deeply uncomfortable realization. Even if humanity were to cease all active messaging tomorrow, even if every radio transmitter on Earth was silenced, and every METI program permanently shuttered, our planet would still be broadcasting its presence through the chemical composition of its air, the spectral signature of its surface, and the thermal emissions of its civilization. Complete invisibility may already be impossible. The question is not whether we can hide, but whether we should be making ourselves louder. The destruction of the Yevpatoria planetary radar in August 2025 adds an unexpected and darkly ironic dimension to this discussion. The facility from which humanity transmitted some of its most powerful deliberate interstellar messages, the cosmic call transmissions that announced our existence to multiple star systems, was not silenced by an alien response or a cosmic catastrophe. It was destroyed by a Ukrainian military drone during the Russo-Ukrainian War. One of humanity's loudest voices to the cosmos was extinguished not by any force from beyond the stars, but by the same species that built it, in a conflict over territory and sovereignty on a single small planet. If there is a metaphor embedded in this event, it is not a comfortable one. A civilization that cannot resolve its own internal conflicts over the distribution of resources on a single world is simultaneously broadcasting its existence and location to a galaxy that may punish that kind of visibility with annihilation. The ongoing absence of international governance over active messaging compounds the problem. As of today, there is no treaty, no binding international agreement, and no institutional framework governing who can transmit signals into space. at what power levels, toward what targets, or with what content. The United Nations Committee on the Peaceful Uses of Outer Space has never taken up the question in a binding capacity. The International Academy of Astronautics has produced voluntary protocols recommending consultation before transmission, but these protocols have no enforcement mechanism and have been repeatedly ignored by METI practitioners who argue that waiting for global consensus would mean waiting forever. This governance vacuum means that the decision to reveal humanity's existence and location to the galaxy has been made, and continues to be made, by small groups of scientists acting on their own initiative. The Arecibo message was transmitted by a team of astronomers without authorization from any governmental body. The cosmic call transmissions were organized by a private company with cooperation from a military facility. METI International operates as a non-profit organization with no formal accountability to any national government or international institution. The decisions these groups have made are irreversible. The signals they have transmitted are already propagating outward at the speed of light. They cannot be recalled, jammed, or retracted. Whatever consequences follow from those signals, they will be consequences for the entire species, not merely for the individuals who press the button. This asymmetry between who decides and who bears the consequences is perhaps the most troubling practical dimension of the METI debate. A handful of people have made a choice that could, under the assumptions of the dark forest, affect the long-term survival of every human being alive and every human being who will ever live. They have done so based on assumptions about the benevolence of the universe that are not supported by evidence, because no evidence exists either way. The absence of evidence for alien hostility is not evidence of alien benevolence. It is simply absence, the same absence that the dark forest theory reinterprets, not as emptiness but as strategy. And yet, condemning these transmissions after the fact accomplishes nothing. The signals are gone. The information is travelling outward at 300,000 kilometers per second. In a very real sense, the experiment has already been conducted. The only question remaining is what the result will be, and the timescales involved mean that humanity may not learn the answer for decades, centuries, or millennia, if an answer comes at all. What the dark forest theory forces us to confront is not the certainty of danger, but the impossibility of certainty itself. We do not know whether alien civilizations exist. We do not know whether they are hostile, peaceful, curious, indifferent, or something beyond our capacity to categorize. We do not know whether our signals will ever be detected by anyone. We do not know whether the dark forest model accurately describes the strategic landscape of the cosmos, or whether it is a pessimistic abstraction that fails to capture the complexity of real civilizational behavior. We do not know any of these things, and the structure of the situation guarantees that we cannot know them in advance. We can only act under uncertainty and live with the consequences. The defenders of active messaging are correct, that fear alone is not a sufficient basis for policy, that the potential rewards of contact are enormous, and that humanity's instinct to reach outward is among the noblest impulses our species possesses. The critics of active messaging are correct, that irreversible decisions with existential consequences deserve more deliberation than they have received, that the absence of evidence is not evidence of safety, and that the chain of logic underlying the dark forest theory is disturbingly resistant to refutation. Between these positions lies a silence that grows more significant with every year that passes without an answer. Not the silence of an empty cosmos, perhaps, but the silence of a cosmos that has learned something about the relationship between visibility and survival. A silence that every unanswered signal from Earth makes more conspicuous. A silence that might mean nothing at all, or might mean everything. The signals we have already sent are beyond recall. The question that remains is not whether we should have sent them. It is what the silence that greets them is trying to tell us, and whether we are wise enough, or humble enough, to consider the possibility that the answer is something we do not want to hear. The most unsettling thing about the dark forest theory is not what it claims. It is what it does not need to claim. It does not need to assert that aliens exist. It does not need to prove that any civilization has ever been destroyed for revealing itself. It does not need to demonstrate that the logic it describes has ever been acted upon by anyone, anywhere, at any point in the history of the cosmos. The theory operates entirely in the conditional. If civilizations exist, and if survival is their primary drive, and if cosmic distances make trust impossible, and if technological development can transform a harmless neighbor into an existential threat within a cosmically insignificant window of time, then the rational equilibrium is silence. The theory does not tell you what the universe is, it tells you what the universe might be, and it asks whether you are comfortable with the size of that might. This conditional quality is precisely what makes the theory so difficult to dismiss and so important to examine honestly. The dark forest is not a proven model of cosmic reality. It is a hypothesis, one among many proposed explanations for the Fermi paradox, and it competes for plausibility with alternatives that are less disturbing, and in some cases, better supported by the limited evidence available. Intellectual honesty demands that we examine the strongest objections to the theory before assessing what weight it should carry in our thinking about our place in the universe. The most fundamental criticism of the dark forest theory targets its assumption about the universality of its logic. The theory treats all civilizations as rational actors operating under identical strategic constraints, converging independently on the same survival calculus. But this assumption may dramatically underestimate the diversity of minds that could emerge across billions of years of independent evolution on billions of different worlds. Human game theory is built on models of decision-making, derived from human psychology, human economic behavior, and human political history. These models may not apply to intelligences that evolved under radically different conditions. Consider the range of cognitive architectures that might exist in a galaxy this old. A civilization might consist of a single vast organism spanning an entire planet, a biological network with no concept of individual identity, and therefore no concept of competition between individuals. A civilization might be a hive intelligence, a collective consciousness in which every member shares complete information with every other member, and decisions emerge through processes that have no analogue in human governance. A civilization might have transcended biological form entirely, existing as patterns of information encoded in magnetic fields or plasma currents, with no need for planets, no concept of territory, and no resource constraints of the kind that drive competition between biological species. A civilization might experience time differently, living so slowly that 1,000,000 years feels like an afternoon, or so quickly that the entire history of human civilization passes in what they perceive as a moment. Each of these possibilities, and countless others that human imagination has not yet conceived, would produce a strategic landscape utterly unlike the one the dark forest theory describes. The theory's critics argue that projecting human competitive instincts onto alien minds is a form of cosmic parochialism, the same mistake that ancient astronomers made when they assumed the Earth was the center of the universe. We are generalizing from one data point, our own species, to make universal claims about the behavior of all possible minds. This is a serious objection. The history of science is littered with examples of theories that seemed logically airtight within their assumptions, but turned out to be wrong because the assumptions themselves were too narrow. A second major criticism concerns the economics of interstellar conflict. The dark forest theory assumes that eliminating a distant civilization is a viable and rational strategy, but the costs of projecting destructive force across interstellar distances might be so enormous that no civilization, however advanced, would find it worthwhile. Accelerating any physical object to a significant fraction of the speed of light requires energy expenditures that dwarf anything humanity currently commands. Sending a fleet or even a single weapon system to a star system tens or hundreds of light years away would consume resources that might be better spent on internal development, expansion into uninhabited systems, or defensive measures. If the cost of destroying a distant civilization exceeds the cost of simply monitoring it and preparing defenses, then the game theoretic calculus shifts away from preemptive strikes and toward watchful coexistence. Furthermore, the universe is not actually resource scarce in the way the theory's second axiom might suggest at first glance. The Milky Way contains hundreds of billions of stars, the overwhelming majority of which show no signs of habitation by technological civilizations. Even if millions of civilizations exist in the galaxy, the number of unoccupied star systems vastly exceeds the number of occupied ones. A civilization seeking additional resources has access to an effectively unlimited supply of uninhabited worlds, asteroids, and stellar energy sources without ever needing to compete with or threaten another civilization. The scarcity assumption that drives competition in terrestrial ecosystems may not apply at galactic scales, where the ratio of resources to claimants is incomprehensibly large. A third objection questions whether the chain of suspicion truly prevents cooperation under all possible conditions. On Earth, cooperation between strangers and even between historical enemies has emerged repeatedly throughout human history, often in situations characterized by significant uncertainty and mutual distrust. International trade, scientific collaboration, arms control agreements, and the establishment of shared institutions like the United Nations all represent cases where parties with conflicting interests and incomplete information about each other's intentions found ways to cooperate despite the risks. Game theorists have demonstrated that cooperation can emerge spontaneously in repeated interactions, even among purely self-interested actors, through mechanisms like reputation building, reciprocal altruism, and the shadow of the future, which makes the long-term benefits of cooperation outweigh the short-term gains of defection. Dark forest proponents respond that these mechanisms depend critically on conditions that do not hold at interstellar scales, specifically the ability to interact repeatedly, communicate quickly, monitor behavior, and punish defection within timeframes short enough to matter. But critics counter that the theory may underestimate the ingenuity of civilizations that have had millions of years to develop solutions to coordination problems. Perhaps advanced civilizations have developed signaling mechanisms, verification technologies, or institutional structures that we cannot currently imagine, solutions that collapse the chain of suspicion and make interstellar cooperation feasible. Ruling out this possibility requires the same kind of assumption about the limits of alien capability that the theory elsewhere insists we cannot make. A fourth criticism comes from an empirical direction. If the dark forest theory is correct, and if civilizations routinely destroy any neighbor that reveals itself, we might expect to see evidence of such destruction in the astronomical record. Gamma-ray bursts, anomalous stellar extinctions, the sudden disappearance of technosignatures from previously active systems. These are the kinds of events that a galaxy governed by dark forest logic might produce. Yet we have observed nothing that clearly indicates deliberate civilizational destruction. The astronomical record is consistent with a universe in which no such events have occurred, which is also consistent with a universe in which no civilizations exist to be destroyed, or one in which destruction is carried out so cleanly that it leaves no detectable trace. The evidence is ambiguous, which is frustrating for both sides of the debate. These criticisms are serious and deserve weight. They demonstrate that the dark forest theory is not the only logically consistent interpretation of cosmic silence, and that its assumptions, while defensible, are not inevitable. The universe may operate according to rules that are kinder, stranger, or more complex than the theory's elegant but stark logic suggests. And yet, the theory persists. It persists not because its proponents are pessimists or misanthropes, but because the specific conditions it identifies as drivers of its conclusion are real features of the universe that no amount of optimism can wish away. Interstellar distances are genuinely vast. Communication delays are genuinely measured in years, decades, and centuries. The intentions of alien minds are genuinely opaque. Technological development genuinely accelerates in ways that can transform a primitive species into a dangerous one within cosmically negligible time periods. And there genuinely exists no enforcement mechanism, no galactic institution, no cosmic police force capable of guaranteeing that agreements between civilizations will be honored. These are not assumptions. They are facts about the physical universe we inhabit. The dark forest theory draws its power not from speculation about alien psychology, but from the structure of the environment in which all civilizations, whatever their psychology, must operate. You can argue that cooperation is possible despite these constraints. You can argue that the costs of interstellar conflict outweigh its benefits. You can argue that the diversity of alien minds makes universal convergence on any single strategy unlikely. All of these arguments have merit, but none of them eliminate the underlying conditions that make the dark forest logic operational. They reduce the probability that the theory describes reality accurately. They do not reduce it to zero. And this is where the emotional weight of the theory truly settles. Because the question it forces you to confront is not whether the dark forest is definitely real. The question is whether you are willing to bet your civilization's existence on the assumption that it is definitely not. This is not a hypothetical wager. It is the wager that humanity is making right now, today. With every signal we transmit and every techno-signature we produce, we are betting that the universe rewards openness. We are betting that the first civilization to detect our signals will be curious rather than cautious, friendly rather than fearful, inclined to respond with a greeting rather than a coordinates-locked weapon. We are betting that the strategic logic of the dark forest does not apply in the real universe, or that it applies but no civilization is close enough to threaten us, or that it applies and civilizations are nearby but have chosen mercy over mathematics. Every one of these bets might be correct, but every one of them is a bet, and the stakes are not abstract. There is a particular kind of horror that comes not from monsters or malice but from logic. It is the horror of a system in which no one needs to be evil for terrible things to happen. The dark forest theory does not require a villain. It does not need a species that delights in destruction or a civilization that conquers for sport. It needs only the conditions that the universe itself provides: distance, uncertainty, the impossibility of trust, and the irreversible consequences of being wrong. Under these conditions, the theory suggests, even a civilization composed entirely of beings who genuinely wish no harm to anyone might conclude that silence is the only responsible choice, and that eliminating a newly visible neighbour is an act not of aggression but of self-preservation. This is the dimension of the theory that is hardest to sit with. It is easy to dismiss a universe full of hostile aliens as a projection of human anxieties onto the cosmos. It is far more difficult to dismiss a universe in which benevolent civilizations are forced by strategic logic into behaviours that look indistinguishable from hostility. The dark forest does not need evil. It needs only rationality applied to an environment where the cost of trust is potentially infinite and the reward for caution is continued existence. And it asks us to consider the possibility that the silence of the cosmos is not a void waiting to be filled with contact and discovery, but a landscape shaped by ancient strategic calculations that we are only beginning to understand. Every civilization that has ever looked outward and wondered whether to announce itself has faced the same decision tree. Broadcast and risk detection. Remain silent and persist in ignorance of your neighbours. The theory proposes that civilizations which chose the first option are no longer around to regret it, while civilizations that chose the second option endure in the darkness, aware of each other only through the shared discipline of saying nothing. If this is true, then the silence we observe when we point our radio telescopes at the sky is not empty. It is full of civilizations that have solved the same problem and arrived at the same answer. Full of species that once felt the same longing for contact that humans feel and learned to suppress it, not out of indifference but out of wisdom. Full of minds that understand something about the relationship between visibility and survival that humanity, in its youthful confidence, has not yet learned. The philosopher Thomas Hobbes described the natural state of human existence before the establishment of social contracts and governing institutions as a war of all against all. Life in this state, he wrote, was solitary, poor, nasty, brutish, and short. The dark forest theory extends this vision to the cosmos and removes the one escape route that Hobbes identified. On Earth, humans escaped the state of nature by forming societies, establishing laws, and creating institutions that could enforce agreements and punish violations. These structures made cooperation rational by changing the incentive landscape, ensuring that the long-term rewards of working together outweighed the short-term temptations of predation. In the cosmos, no such escape route exists. There is no galactic leviathan capable of enforcing order across interstellar distances. There is no cosmic social contract that civilizations can sign, and trust will be honored. The state of nature persists forever, because the conditions necessary to transcend it, proximity, rapid communication, shared institutions, verifiable commitments, cannot be achieved between civilizations separated by light years and linked only by the sluggish medium of electromagnetic radiation. The cosmos, under this reading, is the one place where the Hobbesian nightmare cannot be outgrown. It is permanent, structural, and inescapable. This interpretation of cosmic silence transforms the universe from a place of wonder into a place of warning. It suggests that every star you see in the night sky is a campfire around which someone might be sitting, watching the darkness, trying not to be seen. It suggests that the great empty spaces between stars are not empty at all, but occupied by civilizations that have mastered the art of invisibility because their survival depends on it. It suggests that the question we should be asking is not why the universe is so quiet, but how the universe got so good at being quiet, and what happened to the civilizations that were loud. The theory does not prove any of this. It cannot prove any of this. Proof would require evidence that we do not have and may never obtain. But what it does is something almost more powerful than proof. It provides a coherent, internally consistent, and logically rigorous framework that makes cosmic silence not merely compatible with a populated galaxy, but expected. It turns the Fermi paradox from a mystery demanding exotic solutions into a natural consequence of basic strategic principles applied at cosmic scale. And it does so while requiring fewer assumptions than most competing explanations. Where does this leave humanity? It leaves us in exactly the position we have occupied since we first looked up at the stars, uncertain. We do not know whether the dark forest theory describes reality. We do not know whether the cosmos is a dangerous place for civilizations that make themselves known. We do not know whether our signals have been detected, whether they will be detected, or whether detection would lead to consequences we cannot survive. We are making decisions about our electromagnetic posture, our messaging programs, and our techno-signature management in a state of almost total ignorance about the strategic environment we inhabit. But the theory does one thing that no amount of uncertainty can undo. It forces us to take seriously the possibility that the silence of the cosmos is not an invitation to speak louder, but a warning to speak more carefully. It forces us to consider that the universe may operate according to rules that do not reward the bold and the open, but the cautious and the hidden. It forces us to ask whether the dream of contact that has animated human civilization since the first astronomer pointed a telescope at the stars might be not a noble aspiration but a dangerous illusion, a misreading of the evidence so profound that it could, in the worst case, cost us everything. The universe has not answered our signals. It has not confirmed the dark forest theory. It has not confirmed any theory. It has simply remained silent, as it has been silent for every moment of the 60 years we have been listening and the century we have been inadvertently broadcasting. That silence is consistent with a cosmos that is empty. It is consistent with a cosmos that is full of life, too primitive or too distant to detect. It is consistent with a cosmos governed by physics or biology that makes interstellar communication impossible for reasons we have not yet discovered, and it is consistent with a cosmos in which every surviving civilization has learned, through logic or through bitter experience, that the only way to persist in a universe of armed strangers is to never let anyone know you are there. We cannot distinguish between these possibilities with the information we currently possess, but we can notice something about the last possibility that separates it from all the others. If the universe is empty, our signals do no harm. If the universe is full of life too distant to detect us, our signals do no harm. If interstellar communication is physically impossible, our signals do no harm. But if the dark forest theory is correct, even partially, even approximately, even as a rough description of the strategic landscape that some fraction of civilizations in the galaxy have converged upon, then every signal we send is a risk whose magnitude we cannot calculate and whose consequences we cannot reverse. The rational response to this asymmetry is not to cease all exploration or to abandon the search for extraterrestrial intelligence. It is to approach the cosmos with a degree of humility that humanity has not yet demonstrated. It is to recognize that the decision to announce our existence to the galaxy is not a scientific experiment with controllable variables and reversible outcomes, but an irreversible commitment with stakes that encompass the entire future of Vretu, our species. It is to consider the possibility that the ancient longing to be known, to be heard, to be answered by a voice from beyond the darkness, might be the one impulse that the universe most ruthlessly punishes. The night sky is quiet tonight. It has been quiet for every night of human history. We have interpreted that quiet as loneliness, as emptiness, as an invitation to fill the void with our own voice. But there is another interpretation available, one that does not require us to be alone, one that allows the galaxy to be teeming with life, with intelligence, with civilizations far older and wiser than our own. An interpretation that asks only one small adjustment to our assumptions. What if the quiet is not empty? What if the quiet is full of listeners? What if every civilization in the galaxy arrived, independently and inevitably, at the same conclusion, that the universe is a dark forest, and the first rule of survival is to never make a sound? We are a young civilization, barely a century into our electromagnetic existence, still learning the basic grammar of the cosmos. We have shouted into the dark with the confidence of a species that has never been answered and does not yet know what an answer might cost. The signals are gone. They travel outward at the speed of light, carrying our location, our level of technology, and our extraordinary willingness to be seen. The universe has heard us. Or it has not. We may never know which. But the silence that greets us is no longer just a mystery. It is a message. And the message, if we are brave enough to hear it, might be the most important warning our species has ever received. The cosmos is not necessarily empty. It might be full of civilizations that have learned to survive by mastering a single terrifying discipline: silence.